Chapter 1, Fitting the Academic and Comprehensive Style of the Proposed Encyclopedia Part I, Foundations of Soil Analysis Chapter 1, The Pedosphere, A Complex Natural Resource 11 Introduction to Soil as a Dynamic System 12 Soil Formation Factors and Processes 13 Key Soil Components, Minerals, Organic Matter, Water, and Air 14 The Importance of Comprehensive Soil Analysis in Agriculture, Ecology, and Environmental Science 141 in Agricultural Productivity and Sustainability Nutrient Management. Precision fertilization based on accurate NPK and micronutrient analysis to maximize crop yield, minimize input costs, and prevent nutrient runoff. Soil health assessment, moving beyond basic nutrients to evaluate organic matter content, microbial activity, and soil structure for long-term fertility and resilience. pH and liming requirements, determining the need for soil amendments to optimize nutrient availability and root health for specific crops. Irrigation management, using analysis of soil texture and water holding capacity to inform efficient water use and prevent salinization. 142 in ecological understanding and conservation. Ecosystem functioning, quantifying soil's role in biogeochemical cycling, e.g., carbon, nitrogen cycles, water filtration, and as a foundational component of habitats. Biodiversity monitoring, using biological assays, microbial biomass, enzyme activity, faunal counts, as indicators of ecosystem health and stability. Conservation and restoration, setting baselines and monitoring success in restored landscapes by tracking physical, chemical, and biological soil properties. Forensic pedology, applying mineralogical and geochemical analysis to link soil samples to specific locations for ecological and criminal investigations. 143 in environmental monitoring and remediation. Contaminant detection and risk assessment, identifying and quantifying pollutants, e.g., heavy metals via ICP-MS, organic contaminants via GCMS, to assess risks to human and ecosystem health. Landfill and waste management, monitoring soil and leachate chemistry to ensure containment and prevent groundwater contamination. Remediation design and validation, selecting appropriate cleanup technologies, e.g., phytoremediation, chemical stabilization, based on soil properties and continuously monitoring their effectiveness. Carbon sequestration and climate change mitigation, precisely measuring soil organic carbon stocks and dynamics through techniques like LOI, elemental analysis, and spectroscopic methods to model and verify carbon capture. Chapter 2, Maintaining the rigorous, practical, and encyclopedic style of the work. Part I, Foundations of Soil Analysis. Chapter 2, Principles of Representative Soil Sampling. 21 Site Assessment and Stratified Sampling Strategies. 211 Defining the population and unit of interest, field, plot, management zone, or contaminated site. 212 Pre-sampling reconnaissance, reviewing soil maps, historical land use, remote sensing data, and conducting visual surveys to identify zones of variation, e.g., topography, soil color, vegetation health. 213 Sampling design patterns, simple random sampling, suitable for uniform areas. Systematic sampling, grid essential for spatial variability mapping and precision agriculture. Stratified random sampling, dividing a heterogeneous area into more homogeneous sub-areas, strata, based on factors like soil type, slope, or past management, then sampling randomly within each stratum. This is the most common and statistically robust approach for complex fields. 214 Determining sample number, balancing statistical confidence with practical constraints. Formulas based on desired precision, population variability, and cost. 22 Tools and techniques for sampling at various depths. 221 Hand tools, soil probes/cores, preferred for minimal disturbance and retrieving a defined volume of soil at a specific depth, e.g., 0 to 15 cm, 15 to 30 cm, augers, Dutch, screw, barrel. Useful for deeper sampling or in harder soils, can cause more compression and mixing of layers. Trowels and spades, for bulk samples or sampling from soil pits. For detailed profile description. 222 Depth-specific considerations, plow layer sampling, e.g., 0 to 20 cm, For routine agronomic testing, subsoil sampling, e.g., 30 to 60 centimeters, for nutrient leaching, rooting depth, or contaminant migration studies, composite sampling vs discrete depth sampling, creating one composite sample per stratum vs keeping samples from each depth interval. Separate for analysis 23 sample handling, preparation, and preservation 231 field handling, use clean, non-contaminating containers, polyethylene bags, buckets, composite sampling, taking 15 to 20 subscores from a defined area to form one representative composite sample, immediate field logging, sample ID, date, location, GPS, depth, and visual observations, color, texture, moisture, roots, 232 preservation for specific analyses, microbiological assays, samples must be kept cool, 4 degrees Celsius, and processed within 24 hours to preserve microbial community integrity. Volatile compound analysis, samples must be placed in sealed vials with no headspace and immediately refrigerated or frozen. Nitrate/nitrite analysis, should be frozen or extracted immediately due to rapid biological transformation. 24 subsampling, drying, grinding, and sieving. 241 sample preparation flow, 1 air drying, spreading samples on clean paper trays in a dust-free environment to halt microbial activity. Avoid temperatures 40 degrees Celsius to prevent loss of volatile organics. 2 root and debris removal, picking out large organic and inorganic materials not part of the soil matrix to be analyzed. 3 crushing and grinding, using a mechanical soil grinder or mortar and pestle to break down aggregates. 4 sieving, passing the soil through a standardized sieve, e.g., 2 mm for standard chemical tests, finer meshes for specific analyses like particle size or total elemental digestion. 242 cone and quartering, a standard method for obtaining a representative subsample from a larger, heterogeneous dried sample. The pile is mixed, formed into a cone, flattened, divided into quarters, and opposite quarters are combined and repeated until the desired sample size is achieved. 25 quality assurance and quality control, QA/QC, in the field and lab. 251 QA/QC in the field, equipment decontamination, cleaning tools between samples or strata to prevent cross-contamination, especially critical for trace metal and pollutant studies. Field blanks, submitting containers filled with deionized water to check for contamination during sampling and transport. Duplicate samples, collecting 2 samples from the same location to quantify sampling variability. 252 QA/QC in the laboratory, standard reference materials, SRM certified soils with known properties are analyzed alongside batches of unknown samples to check analytical accuracy. Replicates, analyzing a subset of samples in duplicate or triplicate to measure analytical precision. Spike recovery, adding a known quantity of an analyte to a sample to determine the percentage recovered, checking for matrix interference. Blank analysis, running method blanks, all reagents, no soil, to identify background contamination from the preparation process. 253 documentation and chain of custody, a rigorous system to track sample integrity from collection through analysis to data reporting, which is paramount for regulatory and research purposes. Chapter 3, which serves as the critical bridge between sampling and the specific analytical techniques covered in the rest of the encyclopedia. Part I, Foundations of Soil Analysis. Chapter 3, the analytical framework, choosing the right tool. 31 Defining analytical objectives, what are you measuring and why? 311 The question-driven approach, framing the analysis around a specific, answerable question, e.g., is phosphorus the yield-limiting nutrient, vs. what is the total P content? 312 Common analytical goals, fertility assessment, determining plant available nutrient levels for agronomic recommendations. Environmental contamination, quantifying total or bioavailable concentrations of pollutants. Fundamental characterization, understanding mineralogy, organic matter chemistry, or physical structure for research or classification. Biological health, assessing microbial diversity and activity as an indicator of soil function. 313 Defining the analyte and its form, distinguishing between total content, e.g., total metals via XRF or ICP-MS after digestion, bioavailable/bioaccessible fraction, e.g., exchangeable cations, MELIC3 extractable nutrients, operationally defined fractions, e.g., organic carbon pools separated by density or solubility. 32 Overview of analytical technique categories. 321 Physical techniques, detailed in Part 2. Purpose: characterize the soil's architectural framework. Examples: particle size distribution, laser diffraction, sieving. Bulk density, water retention curves, aggregate stability. 322 Wet chemical/classical techniques, detailed in Part 3. Purpose: quantify specific, often operationally defined, chemical properties through extractions and reactions. Examples: colorimetric assays, No, extraction for exchangeable cations, Walkley black organic carbon, pH and EC pros, well established, often inexpensive, directly tied to historical databases and recommendation systems. Cons: can be time-consuming, generate chemical waste, and measure available pools that are method-dependent. 323 Instrumental and spectroscopic techniques, detailed in Part 4. Purpose: identify and quantify elements, minerals, and organic functional groups based on their interaction with energy. Examples: 4 elements, AAS, ICPOES, ICP-MS, XRF for mineralogy, X-ray diffraction, XRD, for organic/functional groups, mid-IR, near-IR, Raman spectroscopy pros, high throughput, multi-analyte capability, minimal chemical waste. 4. Direct analysis, non-destructive potential. Cons: high capital cost, often requires sophisticated calibration and chemometrics, may measure total rather than available pools. 324 Biological techniques, detailed in Part 2. Purpose: measure the abundance, diversity, and activity of soil organisms. Examples: microbial biomass, soil respiration, enzyme assays, DNA sequencing. Pros: direct measures of soil biological health and function. Cons: methods can be sensitive to handling and storage, highly variable, and complex to interpret. 33 The concept of method integration and triangulation of data. 331 The limitations of a single technique. No one method provides a complete picture of soil health or function. For example, total elemental analysis, XRF, doesn't predict bioavailability, and a chemical test for nitrate doesn't explain the microbial processes producing it. 332 Complementary techniques. Example 1. Using XRD to identify clay minerals and CEC analysis to measure their functional consequence. Example 2. Using loss on ignition, LOI, for a quick SOM estimate and mid-IR spectroscopy to characterize the quality and stability of that organic matter. Example 3. Using ICP-MS to identify metal contamination and sequential extraction methods to determine its potential mobility and environmental risk. 333 Triangulation, the process of using multiple, independent methods to converge on a more robust and reliable conclusion. Agreement between techniques, e.g., near prediction of organic carbon validated by traditional dry combustion, greatly increases confidence in the result. 34 Introduction to data interpretation and statistical analysis. 341 Beyond a number, context is key. Interpreting a result, e.g., 40 mg/kgp, requires context, comparison to established critical values, sufficiency ranges, regulatory thresholds, or baseline values for that soil type. 342 Descriptive statistics, calculating means, medians, standard deviation, and variance to understand the central tendency and variability of your data. 343 Inferential statistics, t-tests and ANOVA, determining if the differences between the means of two or more groups, e.g., managed vs unmanaged fields, are statistically significant. Correlation analysis, identifying relationships between variables, e.g., does clay content correlate with organic carbon? Regression analysis, modeling and predicting one variable based on another, e.g., predicting yield based on soil test potassium, 344 geostatistics, preview of chapter 15, using tools like variography and kriging to interpret spatial data and create interpolation maps from grid sampled points. 345 chemometrics, preview of chapter 14, the application of multivariate statistics, principal component analysis, PCA, partial least squares regression, PLSR, to extract meaningful information from complex chemical data, especially from spectroscopic instruments. Chapter 4, providing the technical depth and practical context expected in an encyclopedia. Part 2, physical and biological characterization techniques. Chapter 4, physical property analysis. 41 particle size distribution, sieve and hydrometer methods vs laser diffraction. 411 the soil separate classes, definition of sand, 20, 005 mm, silt, 005, 0002 mm, and clay, 0002 mm, fractions and their influence on soil behavior. 412 the pipette and hydrometer method, sedimentation principle, based on Stokes' law, which relates the settling velocity of a spherical particle in a fluid to its diameter. Procedure, soil is dispersed, using chemical and mechanical means, and the density of the suspension is measured over time with a hydrometer or via pipette sampling at specific depths. Advantages, standard, reference method, relatively low-cost equipment. Disadvantages, time-consuming, can take 24+ hours, requires skilled technique. Uses chemical dispersants. 413 laser diffraction analysis, principle, particles passed through a laser beam scatter light at an angle inversely related to their size. A detector array measures the scattering pattern, and software calculates the size distribution. Procedure, soil is dispersed in a liquid or air stream and pumped through an optical cell. Advantages, rapid, minutes per sample, high resolution, wide dynamic range, high reproducibility, small sample size. Disadvantages, high instrument cost, results can differ from sedimentation methods due to the principle measuring particle volume rather than settling equivalent diameter, often requires soil-specific calibration. 414 data interpretation and textural class, plotting sand, silt, and clay percentages on a soil texture triangle to assign a textural class, e.g., loam, sandy clay. 42 soil structure, bulk density, porosity, and aggregate stability. 421 bulk density, ρ_b definition, the mass of dry soil per unit volume, including the pore space, G/cm superscript 3, a key indicator of soil compaction. Core method, extracting a known volume of undisturbed soil core, drying it, and calculating mass/volume. Clod method, coating an undisturbed clod in a water-repellent material, saran, and measuring its volume by water displacement. Significance, affects root penetration, water infiltration, aeration, and microbial activity. 422 porosity, definition, the volume percentage of the soil that is not occupied by solids calculated from bulk density and particle density, ρ_p, assume 265 G/cm superscript 3 porosity equals 1, ρ_b/ρ_p, times 100. Pore size distribution, differentiates between transmission pores, drainage, storage pores, water holding, and residual pores. 423 aggregate stability, definition, the ability of soil aggregates to resist disintegration when disrupted by forces like water or tillage. A critical measure of soil structural health. Wet sieving method, sieving soil aggregates underwater and measuring the proportion of water stable aggregates remaining on a sieve. Rainfall simulation, applying simulated rain to a soil surface and measuring splash detachment and crust formation. Significance, high stability reduces erosion, crusting, and enhances water infiltration and aeration. 43 water retention characteristics, pressure plate and tensiometer methods. 431 the soil water characteristic curve, the fundamental relationship between soil water content and the energy with which water is held, metric potential, in kPa. 432 pressure plate extractor, principle, Saturated soil samples are placed on a porous ceramic plate in a sealed chamber. Air pressure is applied to the chamber, forcing water out of the soil pores until it equilibrates at a specific metric potential. Application, used to determine water content at standard potentials like field capacity, approximate -10 to -33 kPa. Water held after gravity drainage. Permanent wilting point, -1500 kPa. Water unavailable to plants. Plant available water capacity, AUC. Calculated as the difference between water content at field capacity and wilting point. 433 tensiometers. Principle, a direct, in situ measuring device consisting of a porous ceramic cup filled with water and connected to a vacuum gauge. As the soil dries, it draws water from the cup, creating a measurable vacuum. Negative pressure. Application, ideal for monitoring real-time soil moisture status in the field, especially in the wet range, 0 to -85 kPa, 44 Atterberg limits. And soil consistency. 441 Definition, a series of tests developed for engineering classification of fine-grained soils based on their water content measures the critical water contents at which a soil transitions between solid, semi-solid, plastic, and liquid states. 442 The three limits. Liquid limit, LL. The water content at which a soil behaves as a viscous liquid measured by the number of blows required to close a groove in a soil pad in a standard cup. Plastic limit, PL. The water content at which a soil can no longer be rolled into a 3 mm diameter thread without crumbling. Shrinkage limit, SL. The water content at which further loss of moisture does not cause a decrease in volume. 443 Derived indices. Plasticity index, pi equals LL, PL. A measure of the range of water content over which a soil remains plastic. High pi indicates high clay content, particularly of expansive smectite clays. 444 Applications, critical for predicting soil behavior in construction, e.g., foundation bearing capacity, slope, stability, shrink swell potential, and interpreting physical behavior in agricultural contexts, e.g., tillage timing, trafficability. Chapter 5, delving into the methods that characterize the living engine of the soil ecosystem. Part 2, physical and biological characterization techniques. Chapter 5, Soil biology and bioactivity assays. 51 Measuring soil microbial biomass, chloroform fumigation and substrate-induced respiration. 511 The concept of microbial biomass, the living component of soil. Organic matter, excluding roots and fauna. 5 μm, acting as both a labile nutrient pool and a catalyst for decomposition. 512 Chloroform fumigation incubation, Phi, and fumigation extraction, Fe. Principle, chloroform vapor lyses microbial cells, releasing their contents in Phi. The fumigated soil is inoculated and incubated. The CO evolved beyond that of a non-fumigated control is proportional to biomass C in Fe. The released C and N are directly extracted with KSO and quantified advantages. Phi is a classic, well understood method. Fe is faster and avoids issues with re-inoculation disadvantages. Phi requires a 10-day incubation. Both methods use toxic chloroform and require conversion factors, Keck and Ken, to calculate actual biomass. 513 Substrate-induced respiration, SIR. Principle, adding an excess of an easily decomposable substrate, e.g., glucose, to soil induces maximum respiratory activity in the microbial community. The initial maximum rate of CO evolution is proportional to active microbial biomass advantages, very rapid, measurement over hours, avoids toxic chemicals. Disadvantages, only measures the active portion of the biomass, response can vary with community structure. 52 Enzyme activity assays as indicators of soil health. 521 The role of extracellular enzymes, catalyze the degradation of organic polymers, e.g., cellulose, chitin, proteins, into smaller molecules that microbes can assimilate. Their activity is a direct measure of functional potential. 522 Common assay types and their significance. Hydrolytic enzymes, related to C, N, P, and S cycling beta-glucosidase, cellulose degradation, C cycle, phosphatase, organic P mineralization, P cycle, N-acetyl beta-glucosaminidase, nag-chitin degradation, C and N cycle, urease, hydrolysis of urea to ammonia, N cycle, oxidoreductase enzymes, involved in humification and degradation of complex aromatics, e.g., phenol oxidase, peroxidase, 523 methodologies, colorimetric assays, using synthetic substrates that release a colored compound upon enzyme cleavage, e.g., p-nitrophenol for phosphatase, fluorometric assays, using methylumboliferyl, MUB, link substrates, which are highly sensitive in situ vs standardized assays, debate between measuring activity in native soil, in situ, vs under optimized conditions, potential activity, for pH and substrate concentration 53 respiration measurements, basal and substrate induced, 531 basal respiration, definition, the steady state rate of CO evolution from soil without added substrates, a measure of the maintenance energy of the heterotrophic microbial community. Interpretation, high basal respiration can indicate high organic matter availability or stress, but must be interpreted in context with biomass. See metabolic quotient, 532 substrate-induced respiration, SIR, as described in 513 for biomass, also a key bioactivity assay, 533 metabolic quotient, QCO calculation, QCO equals basal respiration / microbial biomass. C interpretation, the COC respired per unit of biomass. A high QCO suggests a microbial community under stress, e.g., contamination, disturbance, or one that is inefficient. Are strategists spending more energy on maintenance than growth? 54 molecular techniques, DNA extraction and PCR for microbial community analysis. 541 nucleic acid extraction, the critical first step must efficiently lyse diverse cell types, bacteria, fungi, archaea, while shearing DNA minimally and CO-extracting minimal humic substances, which inhibit downstream reactions. 542 polymerase chain reaction, PCR amplifying target genes from the complex mixture of extracted DNA to detectable levels. Target genes, 16 srRNA gene for bacteria and archaea, its region for fungi. Next generation sequencing, NGS high-throughput sequencing of PCR-AMPL icons to profile microbial community composition, who is there, and calculate diversity indices. 543 quantitative PCR, qPCR used to quantify the absolute abundance of specific taxonomic groups or functional genes, e.g., NIFH for nitrogen fixation, AMOA for nitrification. 544 metagenomics and metatranscriptomics, shotgun sequencing of all DNA, metagenomics, to assess functional potential or all RNA, metatranscriptomics, to assess active gene expression, moving beyond who is there, to what can they do, and what are they doing. 55 nematode and microarthropod counting as bioindicators. 551 extraction methods, nematodes, typically extracted from soil using a Beerman funnel or centrifugal flotation technique. Microarthropods, mites, springtails extracted using Tullgren funnels, Berlese funnels, which use heat and light to drive organisms out of a soil core into a preservative. 552 counting and functional guild classification, nematodes, not just counted, but identified to functional guild based on feeding habits. Bacterivores, fungivores, herbivores, predators, omnivores. Maturity and structure indices, calculated from the ratio of different guilds, e.g., maturity index indicates disturbance, structure index indicates food web complexity. Microarthropods, key players in fragmentation and regulation of microbial populations. Abundance and diversity are strong indicators of system health and complexity. 553 significance, these mesofauna integrate biological, chemical, and physical soil properties over time. Their community structure provides a powerful, holistic bioindicator of ecosystem condition and response to management. Chapter 6, focusing on the foundational wet chemical methods for macronutrient analysis. Part 3, classical and wet chemical techniques. Chapter 6, essential macronutrient analysis. 61 nitrogen, Kagel-Dal digestion, Dumas combustion, and colorimetric method. 611 The nitrogen challenge. Nitrogen exists in numerous soil forms, organic N, NH, No, making total N and available and distinct analytical goals. 612 Kagel-Dal digestion method, total N principle. Soil is digested in concentrated H2O with a catalyst, e.g., Cu, Se, at high heat, 370 degrees C. This process converts organic nitrogen to ammonium, NH, and reduces nitrate/nitrite if a reduction agent is added. Salicylic acid modification. The NH in the digestate is then distilled, trapped in boric acid, and titrated to quantification. Advantages. The historical standard method, robust and reliable for organic rich soils. Disadvantages. Time-consuming, uses large volumes of corrosive and hazardous chemicals, does not recover all nitrate without modification. 613 Dumas combustion method, total N principle. A modern, instrumental approach. Soil is combusted at 1000 degrees C in a pure oxygen environment. All nitrogenous compounds are converted to N gas, which is then measured by a thermal conductivity detector after separating other combustion gases, CO, HO, in a gas chromatograph. Advantages. Faster. 3 to 5 minutes per sample, no hazardous chemicals, automated, includes all forms of N, nitrate, nitrite, excellent precision. Disadvantages. High instrument cost, requires calibration with standards of known N content. 614 Colorimetric methods, inorganic N, NH and No principle. For available N pools, soil is extracted with a salt solution, e.g., 2 mkCl. The extract is then analyzed. Ammonium, NH reacted with salicylate and hypochlorite under alkaline conditions to form a green indophenol. Blue complex, measured by spectrophotometry. Nitrate, No reduced to nitrite, No, via a cadmium or enzymatic column, then reacted with sulfanilamide and N1-naphthyl, ethylene diamine dihydrochloride, NED, to form a pink azo dye. For spectrophotometric detection application, crucial for understanding short-term plant availability and nitrogen cycling dynamics. Often performed on fresh or preserved field moist samples to prevent transformation. 62 Phosphorus, Bray, Olson, and Melick 3. Extractions with spectrophotometric detection. 621 The available P concept. No extractant recovers the exact pool a plant uses. Different extractants are empirically calibrated to crop response in specific soil conditions. 622 Extractant selection based on soil pH. Bray 1 extractant, 003 mNHF plus 0025 mHCl. Target, acidic to neutral soils, pH 70. The fluoride ions dissolve Al and Fe bound P phases. Limitation, ineffective in calcareous soils, high CaCO, as fluoride precipitates as CaF. Olson. Bicarbonate, extractant, 05 mNaHCO, pH 85. Target, neutral to calcareous soils, pH 70. The high pH suppresses Ca solubility, precipitating Ca superscript 2 as CaCO, and dissolves CaP minerals, while also deserving P from Fe and Al oxides. Melick 3 extractant, 02 mCHCOOH plus 025 mNHNO plus 0015 mNHF plus 0013 mHNO plus 0001 mEDDA. Target, a universal extractant designed to work across a wide pH range. The acids dissolve P compounds, F complexes Al and Fe, and EDDA complexes Ca and other micronutrients. Advantage, can be used to extract multiple nutrients, P, K, Ca, Mg, micronutrients, simultaneously for a multi-element test. 623 Spectrophotometric detection, molybdenum blue method principle. The orthophosphate, PO superscript 3, in the extract is reacted with ammonium molybdate and antimony potassium tartrate to form a phosphomolybdate complex. This complex is then reduced by ascorbic acid to form a brilliant blue-colored complex, the intensity of which is proportional to P concentration and measured at 880 nm. 63 Potassium, calcium, magnesium, exchangeable cations via ammonium acetate extraction and AAS/ICP 631. The cation exchange capacity, CEC, concept. These nutrients are primarily held on the negatively charged exchange sites of clay and organic matter. Exchangeable cations are those that can be displaced by another cation. 632. Ammonium acetate extraction, 1-MnHOAC, pH 70 principle. The ammonium ion, NH, is used to displace the native exchangeable cations, K, Ca superscript 2, Mg superscript 2, Na, from the soil colloids. The cations are leached into the solution, which is collected for analysis. pH 70, this buffered pH ensures that acidic cations, Al superscript 3, H, do not dissolve and are not measured as part of the exchangeable base cation pool. 633. Analytical finish, atomic absorption spectroscopy, AAS. The traditional method, the extract is aspirated into a flame. Each element absorbs light at a characteristic wavelength. The amount of light absorbed is proportional to its concentration, potassium, K. Measured by emission mode in the flame due to its ease of excitation. Inductively coupled plasma optical emission spectrometry, ICPOES. The modern, preferred method, the extract is injected into a high-temperature argon plasma, 6000-10,000 K, where atoms are excited and emit light at element-specific wavelengths. ICPOES can measure all cations, K, Ca, Mg, Na, and micronutrients, in the extract simultaneously with high speed and precision. 634. Data interpretation, results, in mol/kg or ppm, are used to assess nutrient sufficiency for crops and to calculate the base saturation percentage of the soil. CEC Chapter 7, covering the critical tests for soil acidity and salinity. Part 3, Classical and Wet Chemical Techniques. Chapter 7, Soil pH, Liming Requirements, and Soluble Salts. 71. Principles of Soil pH Measurement, 1:1 and 1:2. Suspensions, 711. What soil pH represents, a logarithmic measure of the hydrogen ion, H, activity in the soil solution. It is the master variable controlling nutrient availability, microbial activity, and metal toxicity. 712. The electrochemical method, measurement is performed with a pH meter comprising a glass electrode, sensitive to H, and a reference electrode, calibrated using standard buffers, e.g., pH 401, 700, 1001, 713. Standard suspension ratios, soil water, 1:1. The most common routine method, 10 grams air. Dry soil is mixed with 10 ml deionized water, stirred, and let stand for a short period, e.g., 30 to 60 minutes, before measurement. Soil water, 1:2. Used for higher precision or for soils very low in soluble salts. 10 grams soil with 20 ml water. Soil salt solution, e.g., 001 mCaCl. 1:2. Soil to 001 mCaCl solution ratio. This method flocculates colloids, provides a consistent ionic strength, and yields a more stable reading that is typically 0.5 to 0.8 pH units lower than the water pH. It is considered less variable and a better indicator of the potential or reserve acidity. 714. Sources of error, improper calibration, clogged or dried out electrode junctions, insufficient stirring, and the suspension CO equilibrium with the atmosphere. 72. Buffer pH methods for lime requirement, Shoemaker, McLean, Pratt, Sikora, 721. The lime requirement concept, the amount of agricultural limestone, CaCO, needed to raise the pH of a plow layer to a desired target, e.g., pH 65 for most crops. It measures the soil's reserve acidity, H and Al superscript 3 on exchange sites, not just the active acidity in the solution. 722. The buffer principle, a buffered solution with a known initial pH is added to the soil. The soil's acidity neutralizes some of the buffer, causing a pH drop. The magnitude of the pH drop is empirically correlated to the amount of lime required. 723. Shoemaker, McLean, Pratt, SMP, buffer, composition, a double buffer system, p-nitrophenol, triethanolamine, KCRO, acetic acid, etc., with an initial pH of 75. Application, developed for soils with high reserve acidity, high CEC soils containing exchangeable Al, it is the historical standard for acidic, medium to fine textured soils. Procedure: pH of the soil buffer mixture is measured and the drop from 75 is used to consult a calibration table for lime requirement, in ton/acre, 724 Sakura buffer. Composition: a more modern buffer, acetic acid, ammonium acetate, etc., with an initial pH of 68, designed to mimic the effect of lime application, developed as a more universal buffer that performs well across a wider range of soil types, including sandy, low CEC soils where the SMP buffer can overestimate lime need. It is considered more accurate for soils with a significant portion of acidity from organic matter. 725 Choosing a buffer. Laboratory choice is often based on regional soil types and historical calibration data. Some labs may run both or use a modified buffer. 73 Electrical conductivity, EC, for salinity assessment. 731 Principle: the ability of an aqueous solution to conduct an electrical current in a soil saturation extract. The current is carried by dissolved ions, e.g., Na, Cl, Ca superscript 2, so superscript 2, therefore, EC is a direct, aggregate measure of the total concentration of soluble salts. 732 Saturation paste extract method, ES. The standard method: soil is gradually mixed with water until it reaches a saturated paste consistency, shiny, flows slightly, no free water. It is then vacuum extracted, and the EC of the extracted solution is measured using a conductivity cell reported as deci Siemens per meter, ds/m. Y saturation paste, it standardizes the soil-to-water ratio across different soil textures, providing a result that is directly related to the osmotic potential experienced by plant roots. 733 Interpretation and crop impact, non-saline, ES 2 ds/m. Salinity effects negligible. Slightly saline, ES equals 2 to 4 ds/m. Yields of very sensitive crops may be restricted. Moderately saline, ES equals 4 to 8 ds/m. Yields of many crops restricted. Strongly saline, ES equals 8 to 16 ds/m. Only tolerant crops yield satisfactorily. Very strongly saline, ES 16 ds/m. Only a few very tolerant crops yield satisfactorily. 74 Analysis of soluble ions, e.g., Na, Cl, so superscript 2, via ion chromatography. 741 Why specific ions matter. While EC measures total salt content, management decisions, e.g., choosing gypsum vs other amendments, require knowing the specific ion composition. Sodium, Na, causes soil dispersion, degrading structure and permeability, acidic condition, chloride, Cl, and sulfate, so superscript 2 contribute to salinity and can have specific toxicities to plants. 742 Ion chromatography, IC principle: the sample extract is injected into a stream of eluent, a carrier solution, and passed through a series of columns. Separation column contains ion exchange resins that separate anions from cations and then separate individual ions based on their affinity for the resin. Suppressor column chemically suppresses the conductivity of the eluent. Background conductivity detector measures the conductivity of the now separated ions as they elute from the column. Each ion has a characteristic retention time, and the peak area is proportional to its concentration. Application: IC is the premier method for simultaneously quantifying the major soluble anions, Cl, No, So superscript 2, HCO, Po superscript 3, and cations, Na, K, Ca superscript 2, Mg superscript 2, NH, in a soil saturation extract or water sample. 743 Derived parameters: sodium adsorption ratio, SAR, a calculated parameter from the concentrations of Na, Ca superscript 2 and Mg superscript 2 in the extract. SAR equals Na/Ca superscript 2 and Mg superscript 2/2. It predicts the tendency of Na to displace Ca superscript 2 and Mg superscript 2 on exchange sites, which is critical for assessing sodicity hazard. Soil sodicity is defined by a combination of high ESP, exchangeable sodium percentage, and high SAR in the extract. Chapter 8, focusing on the critical methods for quantifying and characterizing soil organic matter. Part 3, Classical and Wet Chemical Techniques. Chapter 8, Soil Organic Matter Characterization. 81 Walkley Black Wet Oxidation Method. 811. Principle: a rapid, wet chemistry oxidation technique that estimates soil organic carbon, SOC, content by measuring the amount of organic matter consumed by a potent oxidizing agent. The method involves digesting the soil with a mixture of potassium dichromate, KCRO, and sulfuric acid, HSO, at a specified temperature. The heat of dilution from the sulfuric acid provides the necessary reaction energy. 812 The oxidation reaction: the dichromate ion, CRO superscript 2, which is orange, is reduced to the chromic ion, Cr superscript 3, which is green, as it oxidizes organic carbon to carbon dioxide. 813 Quantification, back titration method: the excess, unreacted dichromate is titrated with a reducing agent, ferrous ammonium sulfate, Phos. The amount of dichromate consumed in the reaction is calculated from the difference and used to determine the organic carbon content. Colorimetric method: the change in color intensity, from orange to green, can be measured spectrophotometrically to estimate the amount of reduced chromium and thus the carbon oxidized. 814 Limitations and correction: incomplete oxidation: the method does not fully oxidize all organic carbon, typically 75 to 85% recovery, therefore, a correction factor, often 132 or 133, is multiplied by the result to estimate total organic carbon. Hazardous waste: uses large quantities of concentrated sulfuric acid and carcinogenic chromium compounds, generating hazardous waste. Interferences: can be affected by the presence of chloride ions, from saline soils, and inorganic reducing agents, e.g., Fe superscript 2, Mn superscript 2, 82 Loss on ignition, LOI, technique. 821 Principle: a simple, thermogravimetric method that estimates soil organic matter, SOM, content by measuring the mass loss upon combustion of a dry soil sample at high temperature. The mass loss is primarily due to the combustion of organic matter and the dehydration of clay minerals. 822 Standard procedure: 1. A crucible with a known weight of oven dry, 105 degrees Celsius, soil is weighed. 2. The sample is placed in a muffle furnace and ignited at a high temperature, typically 375 degrees Celsius or 550 degrees Celsius, for a set duration, e.g., 2 to 16 hours. 3. The crucible is cooled in a desiccator and reweighed. The mass loss is calculated. 823 Temperature considerations: LOI at 375 degrees Celsius, avoids structural dehydration of certain clay minerals, e.g., kaolinite, gibbsite, but may not combust all stable organic compounds completely. LOI at 550 degrees Celsius, the more common temperature ensures more complete combustion of organic matter but causes the loss of structural water from clay minerals, leading to a potential overestimation of SOM. Carbonates also decompose at this temperature, so the method is not suitable for calcareous soils without a separate acid pretreatment. 824 Conversion to organic carbon: the mass loss on ignition is reported as % SOM. To convert to soil organic carbon, SOC, the result is typically divided by 1724, the Van Bimmelen factor, based on the assumption that SOM is 58% carbon. This factor is now known to be highly variable. Conversion factors of 18 to 25 are often more accurate. 825 Advantages and disadvantages: advantages: inexpensive, requires no hazardous chemicals, can process many samples at once. Simple. Disadvantages: less accurate than dry combustion, not suitable for calcareous or volcanic soils without modification. The conversion factor is a significant source of error. 83 Introduction to soil organic carbon fractionation. 831 The need for fractionation, bulk SOC measurements, Walkley Black, LOI. Dry combustion: treat SOM as a single pool. However, SOM is a complex continuum of materials with vastly different turnover times, from days to millennia, Fractionation aims to separate some into functional pools based on physical or chemical properties to better predict its behavior and function. 832 Physical fractionation, particle size fractionation, separating some associated with different mineral particle sizes, e.g., sand, silt, clay, by dispersion and sieving/centrifugation. The fine silt and clay fractions are associated with more stable, mineral-associated organic matter, MAOM, density fractionation, using a heavy liquid, e.g., sodium polytungstate, to separate, free particulate organic matter, FPOM. Light fraction, 16 to 20 g/cm superscript 3, consisting of undecomposed plant debris. It is a labile, fast cycling pool occluded particulate organic matter, OPOM, found within soil aggregates, with intermediate stability mineral-associated organic matter, MAOM. The heavy fraction, 16 to 20 g/cm superscript 3. Consisting of organic compounds strongly sorbed to clay surfaces. It is a stable, slow-cycling pool. 833 Chemical fractionation, using specific solvents to extract operationally defined pools based on solubility. Hot water extractable carbon, HWC, a sensitive indicator of readily mineralizable carbon and a labile organic pool related to microbial activity. Acid hydrolysis, using strong acid to separate a labile hydrolyzable fraction from a recalcitrant non-hydrolyzable fraction. 834 Significance, fractionation provides insights into carbon sequestration potential, nutrient cycling rates, and soil health dynamics that are masked by a single total SOC value. It bridges the gap between basic quantification and advanced spectroscopic characterization, covered in Part 4, Chapter 9, which covers the critical concepts of soil charge and nutrient retention capacity. Part 3, Classical and Wet Chemical Techniques. Chapter 9, Cation Exchange Capacity, CEC, and Exchangeable Acidity. 91. Summation of cations method. 911 Principle, this method calculates the effective cation exchange capacity, ECEC, which is the CEC measured at the soil's native pH. It is determined by summing the charges of the base cations, Ca superscript 2, Mg superscript 2, K, Na, and the acidic cations, Al superscript 3 and H, often reported as exchangeable acidity. 912 Procedure, 1. Extraction of base cations. The exchangeable base cations are displaced using a neutral, unbuffered salt solution like 1M ammonium acetate, NHOAC, or 1M barium chloride, BaCl. The concentrations of Ca, Mg, K, and Na in the extract are measured via AAS or ICPOES. Extraction of acidic cations. A separate soil sample is leached with 1M potassium chloride, KCl. The KCl solution displaces exchangeable Al superscript 3 and H ions. The concentration of Al superscript 3 in the extract is measured, and the H concentration is often determined by titration of the extract. 913 Calculation, ECEC, mol/kg, equals exchangeable Ca plus Mg plus K plus Na plus exchangeable acidity, Al superscript 3 plus H. The concentrations of individual cations must be converted from ppm or mg/kg to milliequivalents per 100 grams, mol/kg, by dividing by their equivalent weights. 914 Application and interpretation. The ECEC is highly relevant for acid soils, pH 55, where significant exchangeable Al superscript 3 and H are present. It represents the actual CEC operating under field conditions and is used to calculate base saturation, a key metric for liming decisions. 915 Base saturation, BS%. Calculation, BS% equals, sum of base cations/ECEC, times 100. A low BS% indicates an acidic soil that may benefit from liming. 92 Ammonium acetate saturation, at pH 70, method. 921 Principle, this is the most common method for determining the potential CEC of a soil. The soil is saturated with ammonium ions, NH, at a buffered pH of 70. The NH displaces all exchangeable cations, both base cations and acidic cations. The amount of NH retained on the exchange sites is then measured. 922 Saturation and Removal of excess salt. 1. The soil is repeatedly leached with a pH 70, 1 m ammonium acetate, NaOAC, solution until the effluent contains no other cations, e.g., no more Ca superscript 2 is detected. 2. The excess NaOAC salt is then removed by washing with a volatile solvent, typically 95% ethanol. 923 Displacement and quantification. The ammonium-saturated soil is now leached with a solution containing a cation that will displace the NH. The two most common displacing solutions are potassium chloride, KCl. The displaced ammonium, NH, in the leachate is measured by distillation and titration or by colorimetry. The indophenol blue method, sodium chloride, NaCl, less common, but can be used. 924 Application and limitation. This method measures the CEC at pH 70, which is a standard condition that allows for comparison between soils. It is excellent for neutral and alkaline soils. However, for highly acidic soils, it can overestimate the effective CEC because it forces the dissociation of functional groups, on organic matter and some clays, that are protonate and non-exchangeable at the soil's native pH. It does not account for the pH-dependent charge. 93 Barium chloride compulsive exchange method. 931 Principle, a more modern, single extraction method that can determine both the effective CEC and the exchangeable cation composition. It is particularly advantageous for soils with variable charge. 932 Compulsive exchange process. 1. The soil is leached with a 0,1 m or 0,2 m barium chloride, BaCl. Solution. The Ba superscript 2 ion displaces all native exchangeable cations, Ca superscript 2, Mg superscript 2, K, Na, Al superscript 3, H, into the solution, which is collected and analyzed via ICPOES. The sum of these cations is the effective CEC, ECEC. 2. The soil is now saturated with Ba superscript 2. 3. The Ba saturated soil is then leached with a magnesium sulfate, MgSO, solution. This step performs the compulsive exchange. The Mg superscript 2 compulsively exchanges with the Ba superscript 2 on the exchange sites. The amount of Ba superscript 2 displaced is measured and is equivalent to the CEC at the pH of the BaCl solution. 933 Advantages. It avoids the use of buffered solutions, providing a value closer to the field condition, like ECEC, but with a robust methodology. It uses a single soil sample to determine both the exchangeable cation suite and the CEC. Barium is a very strong displacing cation, ensuring complete exchange. It is well suited for soils with significant pH-dependent charge, e.g., highly weathered oxisols, ultisols, and volcanic soils. 934. Disadvantage. Barium chloride is toxic and requires careful disposal. Chapter 10, which covers the core instrumental methods for elemental analysis in soil science. Part 4, Instrumental and spectroscopic techniques. Chapter 10, Elemental analysis via atomic spectroscopy. 101 Principles of atomic absorption spectroscopy, AAS flame and graphite furnace. 1011 Fundamental principle. AAS measures the concentration of a specific element by exploiting the phenomenon that ground state atoms of the element can absorb light at a characteristic wavelength. The amount of light absorbed is proportional to the concentration of the element in the sample, following the Beer-Lambert law. 1012 Instrument components. Light source, a hollow cathode lamp, HCl, or electrodeless discharge lamp, EDL, that emits the specific wavelength of light unique to the element being analyzed. Atomizer, a device to convert the sample into a cloud of free, ground state atoms. Monochromator, isolates the specific wavelength from the light source. Detector, measures the intensity of the light after it has passed through the atomized sample. 1013 Flame atomic absorption spectroscopy, FOS. Atomizer, a premix burner where the liquid sample is nebulized and mixed with fuel, acetylene, an oxidant, air or nitrous oxide, and burned in a flame. 2100-2800 degrees C. Applications, ideal for measuring major and minor elements in soil extracts, e.g., K, Na, Ca, Mg, Fe, Mn, Cu, Zn from ammonium acetate or melic 3 extracts. It is robust, relatively inexpensive, and easy to use. Limitations: relatively high detection limits, mg/L or ppm range, sample is consumed quickly, cannot measure multiple elements simultaneously. 1014 Graphite furnace atomic absorption spectroscopy, GFAS atomizer, a small, electrically heated graphite tube where a microliter volume sample is deposited. The tube is heated through a temperature program, drying, ashing, atomization, to create a transient cloud of atoms. Applications: used for trace elements, e.g., Cd, Pb, as, Se, in soil digests where concentrations are very low, G/L or ppb range. It offers extremely low detection limits due to the efficient atomization and confinement of the sample. Limitations: slower than FAS, more susceptible to matrix interferences, requires matrix modifiers, higher operational complexity and cost. 102 Principles of inductively coupled plasma optical emission spectrometry, ICPOES, 1021 Fundamental principle, ICPOES, or ICPEs, uses a high temperature argon plasma, 6000-10,000 K, to atomize and excite electrons in the sample's atoms. As the excited electrons return to lower energy states, they emit element-specific wavelengths of light. The intensity of this emitted light is measured and is proportional to the element's concentration. 1022 The inductively coupled plasma, ICP, torch, the heart of the instrument. Argon gas flows through a series of concentric quartz tubes surrounded by a radio frequency, RF, coil. A spark ionizes some argon, and the resulting ions and electrons are accelerated by the RF field, colliding with other argon atoms to sustain a stable, toroidal plasma. 1023 Sample introduction and analysis. The liquid sample, e.g., soil digest or extract, is pumped into a nebulizer, creating a fine aerosol which is injected into the plasma base. The elements are simultaneously atomized and excited. 1024 Advantages over AAS. Simultaneous multi-element analysis can measure dozens of elements in a single sample run in less than a minute. Wide dynamic linear range can measure concentrations from low ppb to high ppm without dilution. Low chemical interferences. The high temperature of the plasma minimizes many of the chemical interferences common in AAS. Robustness, excellent for analyzing complex matrices like soil digests. 1025 Applications. The workhorse for multi-element analysis in soils, used for total elemental analysis after digestion and for measuring a wide suite of elements in soil extracts, e.g., P, S, B, and all metals in a single MELIC 3 run. 103 Inductively coupled plasma mass spectrometry, ICP-MS, for ultratrace elements and isotopes. 1031 Fundamental principle. ICP-MS also uses an argon plasma to atomize the sample. However, instead of measuring emitted light, the plasma serves to ionize the atoms. These ions are then separated and quantified based on their mass-to-charge ratio, m/z, by a mass spectrometer. 1032 Instrument components. ICP source functions as in ICPOES but is operated at higher vacuum interface, a series of cones, sampler and skimmer, that extracts ions from the high-temperature plasma into the high-vacuum mass spectrometer. Mass spectrometer, typically a quadrupole mass filter that rapidly scans across a range of m/z values to separate the ions. Detector, an electron multiplier that counts individual ions, providing exceptional sensitivity. 1033 Key advantages and capabilities. Extremely low detection limits, parts per trillion, ppt, level detection for most elements, making it 100 times more sensitive than ICPOES. Isotopic analysis, can measure specific isotopes, e.g., CD114, Pb208, enabling isotope dilution quantification, the most accurate method, and tracer studies. Rapid multi-element analysis, similar speed to ICPOES. 1034 Challenges. Spectral interferences, polyatomic ions from the plasma gas and matrix, e.g., ARC on Fe, ARO on Fe, CLO on V, can overlap with analyte masses. These are mitigated using collision/reaction cell, CRC technology or high-resolution magnetic sector instruments, non-spectral interferences, matrix effects, suppression or enhancement of signal from high-dissolved solids, e.g., from soil digests, mitigated by dilution, internal standardization, and careful calibration. 1035 applications, analysis of ultra-trace toxic elements, e.g., CD, Hg, Tl, U, precious metals, and rare earth elements in soils, essential for environmental monitoring where regulatory thresholds are very low. 104 sample digestion. 4. Total elemental analysis, microwave-assisted acid digestion. 1041 The goal of total digestion, to completely break down the soil matrix, silicates, organic matter, and bring all elements of interest into solution for accurate analysis by ICPOES/MS or AAS. 1042 Acid mixtures, the choice depends on the target elements and soil composition. Aquaregia, 3:1 HClHNO, a strong oxidizer good for near total extraction of many trace metals but does not fully digest silicates, often used for regulatory compliance testing. EPA method 3052, uses a mixture of HNO and HF, plus often HCl or HO, hydrofluoric acid. HF, is essential for breaking down silicon-based, silicate, minerals, which constitute the majority of most soils. This is a true total digestion method. 1043 Microwave digestion principle and advantages. Principle, samples and acids are placed in sealed, pressurized Teflon vessels. Microwave energy heats the mixture rapidly and uniformly. Advantages over hot plate digestion. Speed, digestion is completed in minutes instead of hours. Safety, the closed vessel system prevents loss of volatile elements, e.g., Hg, as, Se, and contains hazardous acid fumes. Efficiency, higher temperature and pressure achieved in the vessel improve digestion efficiency, especially for refractory minerals. Throughput, automated systems can digest 8 to 16 samples simultaneously. 1044 Critical considerations. HF is extremely hazardous and requires specialized training and Teflon labware. After digestion with HF, the digest must be treated with boric acid to complex excess fluoride ions and prevent precipitation of fluorides and corrosion of glassware. In the instrument chapter 11, which covers the techniques that analyze the interaction of light with soil molecules to determine their composition and structure. Part 4, Instrumental and Spectroscopic Techniques. Chapter 11, Vibrational Spectroscopy, IR and Raman. 111 Mid-infrared spectroscopy, mere principles and interpretation of spectra. 1111 Fundamental principle. Mere spectroscopy probes the fundamental vibrational modes of molecules when IR radiation, wave numbers 4000 to 400 cm superscript 1, matches the energy of a specific molecular vibration, stretching, bending, it is absorbed. The resulting spectrum is a fingerprint of the functional groups, e.g., O, C equals O, SiO, present in the sample. 1112 Spectral interpretation for soils. Key absorption bands provide critical information on soil composition, clay minerals, strong SiO stretches and bends, 1000 to 1030 cm superscript 1, 520 cm superscript 1, 470 cm superscript 1, Al-Alo bends, 920 cm superscript 1, and interlayer water, 1630 cm superscript 1, 3400 cm superscript 1, soil organic matter, SOM aliphatic CH stretches, 2920, 2850 cm superscript 1, carbonyl C equals O stretch, 1720 cm superscript 1, amide IN2 bands, 1650, 1550 cm superscript 1, and broad OH stretches, 3400 cm superscript 1, carbonates, strong, characteristic CO stretch bands near 1420 cm superscript 1 and 875 cm superscript 1. 1113 Qualitative vs quantitative analysis. MIR is excellent for identifying mineral types and organic functional groups with robust Chemometric calibration. It can also be used for quantitative prediction of soil properties, e.g., SOC, clay content, carbonate, 112 diffuse reflectance infrared Fourier transform spectroscopy, drifts, 1121 overcoming the limitations of transmission. Traditional transmission IR requires preparing pellets with KBR, which is difficult for absorbing. Scattering samples like soil drifts is a reflectance technique designed for such samples. 1122 principle, IR radiation is directed onto a neat, powdered soil sample. The light penetrates a few micrometers, is absorbed, and scatters in all directions. The diffusely reflected light is collected and measured. 1123 The Kuebel-Comunc transformation, the raw reflectance, R, data is transformed into a pseudo-absorbance value F, R, equals, 1, R, superscript 2/2R to produce spectra that resemble traditional absorption spectra and are linear with concentration. 1124 Advantages, requires minimal sample preparation, just grinding, non-destructive, highly sensitive to surface properties. It is the most common method for acquiring mere spectra of soils. 113 Near-infrared spectroscopy, NIR, for rapid property prediction. 1131 Fundamental principle, NIR spectroscopy measures overtones and combinations of the fundamental vibrations seen in the MIR region. The primary absorbers in this region, 700-2500 nm Oregon, 14000-4000 cm superscript 1, are bonds involving hydrogen, OH, NH, CH. 1132 Spectral features, NIR spectra have broad, overlapping peaks, making direct interpretation by nearly impossible. The power of NIR lies not in identifying specific peaks but in using the entire spectral signature. 1133 The calibration process, chemometrics 1. A large set of soil samples is analyzed using both NIR and traditional reference methods, e.g., dry combustion for C, laser diffraction for clay. 2. Multivariate statistical techniques, primarily partial least squares regression, PLSR, are used to build a mathematical model that correlates the spectral data to the reference data. 3. This calibration model is then used to predict the property of interest in new, unknown samples based solely on their NIR spectrum. 1134 Applications and advantages, speed. Analysis can be completed in under a minute. Multi-parameter prediction, a single scan can predict SOC, clay content, moisture, CEC, pH, and more, simultaneously non-destructive and green, no chemicals required. Field deployment, portable NIR spectrometers enable real-time, on-the-go sensing. 1135 Limitations, totally reliant on accurate calibration models, cannot identify specific compounds, less sensitive than MIR for many components. 114 Raman spectroscopy for mineral and organic compound identification. 1141 Fundamental principle, a complementary technique to IR. It measures the inelastic scattering of monochromatic light, usually a laser. Most light is scattered at the same energy, Rayleigh scattering, but a tiny fraction loses or gains energy corresponding to molecular vibrations, Raman scattering. 1142 Key differences from IR, selection rules. IR requires a change in dipole moment, while Raman requires a change in polarizability. This makes them complementary. Some vibrations are IR active, some are Raman active, some are both. Sample preparation, minimal, can analyze through glass or water, and even individual soil particles under a microscope. Spectral range, Raman spectra are typically plotted in a range similar to MIR, 4000 to 400 cm superscript 1, but look different. 1143 Applications in soil science. Mineral identification, excellent for identifying iron oxides, hematite, goethite, titanium oxides, rutile, anatase, and carbonates, calcite, dolomite, which have strong Raman signals. Organic compounds, can detect specific organic pollutants, e.g., polycyclic aromatic hydrocarbons, and some soil organic matter components. Microscale analysis, Coupling with a microscope, micro-Raman, allows for the characterization of specific microsites, coatings, and inclusions within a soil sample. 1144. Major challenge: fluorescence. Natural organic matter in soil often fluoresces when excited by a laser, overwhelming the much weaker Raman signal. This can be mitigated by using longer wavelength lasers, e.g., 785 nm, 1064 nm, or advanced techniques like surface-enhanced Raman spectroscopy, SERS, Chapter 12, which covers the powerful X-ray techniques used to determine both elemental composition and mineralogical structure of soils. Part 4, Instrumental and Spectroscopic Techniques. Chapter 12, X-ray Techniques. 121 X-ray fluorescence, XRF principles and applications, portable and benchtop. 1211 Fundamental principle: when a high-energy X-ray beam, primary radiation, strikes a sample, it can eject an inner shell electron from an atom to stabilize. An electron from an outer shell drops into the vacancy, emitting a fluorescent X-ray with an energy characteristic of that specific element. The intensity of this emission is related to the element's concentration. 1212 Energy dispersive XRF, ed. XRF, the most common type, especially for portable systems. All emitted fluorescent X-rays are collected simultaneously by a solid-state detector, e.g., SI, Li, which separates them by energy advantages: fast, simultaneous multi-element analysis, simple operation; disadvantages: lower spectral resolution compared to WDXRF, leading to potential peak overlaps. 1213 Wavelength dispersive XRF, WDXRF, typically found in high-end benchtop systems. The emitted X-rays are diffracted by an analyzing crystal before reaching the detector, separating them by wavelength advantages, superior spectral resolution and lower detection limits, more accurate for complex matrices. Disadvantages: slower sequential analysis, more expensive and complex instrumentation. 1214 Applications: portable XRF, PXRF, used for in situ, rapid field screening for soil contamination, e.g., PB, as, CD, ZN, precision agriculture nutrient mapping, and soil textural classification based on elemental proxies. Benchtop XRF, used for high-precision quantitative analysis of major and trace elements in prepared soil samples, powder pellets or fused beads, for total elemental composition, often serving as a reference technique. 1215 Limitations: generally poor sensitivity for light elements, Z11, e.g., C, N, O. Results can be affected by particle size, moisture, and matrix effects, requiring careful calibration. 122 X-ray diffraction, XRD, for quantitative mineralogical analysis. 1221 Fundamental principle, Bragg's law. XRD identifies crystalline phases by exploiting their long-range atomic order. When a monochromatic X-ray beam hits the regular atomic planes within a crystal lattice, constructive interference, a diffraction peak, occurs only at specific angles where the path difference is an integer multiple of the wavelength, n lambda equals 2d sin. Each mineral has a unique set of d spacings, acting as a fingerprint. 1222 Qualitative analysis: the resulting pattern of diffraction peak positions, 2 theta angles, and intensities is compared to a database of known mineral patterns, ICDD PDF4+, for identification. This is the primary method for determining the clay, silt, and heavy mineral fractions of a soil. 1223 Sample preparation, random powder mount, for general identification of non-clay minerals. Oriented clay mounts: clay-sized particles are separated, saturated with specific cations, Mg superscript 2, K, and analyzed air-dried, ethylene glycol solvated, and after heating. This is essential for identifying specific clay minerals, e.g., smectite, vermiculite, kaolinite, chlorite, based on their expansion and contraction behavior. 1224 Quantitative analysis, QXRD, estimating the relative abundance of minerals in a mixture. Methods include reference intensity ratio, RIR, comparing peak intensities to a known internal standard, e.g., corundum, Rietveld refinement, a powerful full pattern fitting method that uses a crystal structure model to calculate a theoretical diffraction pattern and iteratively adjusts scale factors and other parameters until it matches the observed pattern. This is the most accurate modern method for QXRD 1225 applications, fundamental for understanding soil genesis, weathering processes, nutrient retention, via clay mineralogy, physical behavior, shrink swell potential of smectite, and contaminant sequestration. 123 synchrotron-based X-ray techniques for microscale analysis. 1231 The synchrotron light source, a large-scale facility that produces extremely intense, tunable, and coherent beams of X-rays by accelerating electrons to near light speed and bending their path with magnets. This brilliance enables techniques impossible with lab-based X-ray tubes. 1232 Micro X-ray fluorescence, mu-XRF principle, focuses the synchrotron X-ray beam to a micron-sized spot to map the distribution of elements across a soil sample, e.g., a thin section or aggregate. Application, visualizing the co-location of elements, e.g., Zn and P on a fertilizer granule, Pb and Fe on a soil particle, identifying hotspots of contamination, and studying rhizosphere chemistry. 1233 Micro X-ray absorption spectroscopy, mu-XAS principle, includes XANS, X-ray absorption near edge structure, and EXAFS, extended X-ray absorption fine structure. By tuning the X-ray energy across the absorption edge of a specific element, it provides information on that element's chemical speciation, e.g., oxidation state of Cr or As, and local molecular environment, e.g., what atoms are surrounding the target element. Application, determining if a metal is in a toxic or benign form, understanding the molecular scale mechanisms of contaminant sequestration by soil minerals or organic matter. 1234 Micro X-ray diffraction, mu-XRD principle, performs XRD on the same micron-sized spot defined by the synchrotron beam. Application, identifying the specific mineral phase that is hosting a contaminant element identified by mu-XRF, directly linking composition to mineralogy at the microscale. 1235 Computed microtomography, mu-CT principle, takes a series of 2D X-ray radiographs of a sample as it is rotated, then computationally reconstructs a 3D image of its internal structure based on X-ray attenuation. Application, quantifying soil pore network geometry, root soil interactions, aggregate hierarchy, and fluid flow processes in 3 dimensions at micron resolution. 1236 Significance, synchrotron techniques transform soil science from bulk analysis to a microscale, process-based understanding, revealing the chemical and physical interactions that govern behavior at their fundamental scale. Chapter 13, which covers techniques that separate complex mixtures or analyze properties through thermal decomposition. Part 4, Instrumental and Spectroscopic Techniques. Chapter 13, Thermal and Separation Techniques. 131 Thermal Analysis, Differential Scanning Calorimetry, DSC, and Thermogravimetric Analysis, TGA. 1311 Principle of Thermal Analysis, a suite of techniques that measure physical and chemical properties of a sample as a function of temperature under a controlled atmosphere. In soil science, this primarily characterizes organic matter and mineral constituents based on their thermal stability. 1312 Thermogravimetric Analysis, TGA principle, measures the mass change of a sample as it is heated at a controlled rate. Mass losses correspond to the volatilization or decomposition of components, e.g., moisture loss, organic matter combustion, dehydroxylation of clays, decomposition of carbonates. Derivative TGA, dTg. The first derivative of the TGA curve, dm/dt, is often plotted, making it easier to identify the precise temperature at which mass loss rates are maximized. Application in soils, quantification of soil organic matter, SOM mass loss between 150-550 degrees C, though this overlaps with clay dehydroxylation, identification of clay minerals, the temperature and intensity of dehydroxylation, loss of O groups, around 400 to 600 degrees Celsius is characteristic of specific clay types, e.g., kaolinite vs smectite, quantification of carbonate minerals, sharp mass loss due to decarboxylation, release of CO, from calcite, 550-750 degrees C, and dolomite, 750-900 degrees C, 1313 differential scanning calorimetry, DSC principle, measures the heat flow difference between the sample and a reference material as a function of temperature. It detects endothermic, heat absorbing, e.g., melting, decomposition, and exothermic, heat releasing, e.g., combustion, crystallization. Processes application in soils, characterizing soil organic matter, different SOM fractions, label vs stable,